Yeah, I'll just kind of get started. And thank you, Jacob, for kind of the presentation of what I'm sort of going to be going over. And that is pretty much vector databases in computer vision and how they're kind of changing up the field. So let's get started. So I'll first kind of go over what I'm going to be talking about. First, I'm going to go over what a vector database is and why it's different, why it's important, why it's pretty hard to do, and where you can kind of use it. Next, we're going to go over one of the most common use cases of vector databases. This was up until LLMs kind of took the floor, but before that, it was probably the most important use case, which is reverse image search. And the next thing we're going to talk about is kind of the next step in computer vision and vector databases, which is reverse video search, a much harder problem. And then lastly, I'll follow up with a quick demo. It should be working. I was running into some errors before, but I think I fixed that all up, but we'll see. So a little bit about myself. My name is Filip. I'm a software engineer at Zilliz for the last 2.5 years. Kind of been wearing a lot of hats there, worked on a lot of different projects with a lot of different users, customers, open source projects, etc. And those are my contact links. A little bit about Zilliz. We were founded in 2017 and are headquartered in Redwood Shores, so in the Bay Area. We've been in the unstructured data business for quite a while now. We have a few projects that took off pretty well, with the main one being Milvus, which is our vector database, TOE, which is our unstructured data ETL project, GPT Cache, which is a caching service to reduce calls to the large language model providers, and VDB Benchmark, which just kind of compares all those latest vector databases that everyone's been hearing about. So let's first go over what a vector database is and sort of what its role in computer vision is. So the definition of a vector database in kind of my eyes is a database that is purpose-built to store, index, and query vector embeddings that we generate from unstructured data. And what unstructured data is pretty much data that's hard for the computer to compare. A popular one, and I guess that kind of revolves around this talk, is images. Images, although structured in the sense that you know how many pixels they have and what the pixel values can range from, if you sort of move an image by, let's say, 3 pixels across, when you look at the entire image, data-wise, it's going to completely change. Also, if you rotate the image you can't compare directly anymore because all the values are different and will be viewed as completely different. A few other modalities of this are text, video, audio, and pretty much any medical data that you might see. A lot of this data isn't easily comparable by computers. And why it is now is because of deep learning models. We've gotten a lot of models that can take any kind of data, train it up, and then by cutting off the last layer, if it's a classification model, we can get their embeddings, kind of their reasoning for whatever they classify. And this works pretty well for semantic comparison. It's something that's easily comparable by computers. You can calculate distances. And with those distances, you can figure out how similar two objects are. And a few types of models that are useful in this are autoencoders, CNNs, transformers. Pretty much any type of model that inserts data and makes a decision off it, you can kind of modify it to generate some pretty good embeddings. So why a purpose-built vector database and kind of what does it need to offer? So these are the main kind of capabilities that you need to be considered a vector database. And the reason you sort of need a vector database and you can't just use a regular database is because a lot of regular relational databases won't really work well in these high dimensional spaces. Sure, you can store all your vectors as columns and do brute force searches, but this doesn't really scale. Doing brute force searches, sure, it's possible on sub 1 million searches, but after that, you're going to start seeing a lot of problems. It's also difficult to scale out horizontally. There's not as much analytics capabilities, and also there aren't really any good indexing structures that work well in relational databases for vector data. And just a little why Milvus. This is a little overview of our structure. It's a cloud-oriented system. We redesigned it specifically for the cloud to kind of separate computation and storage. This makes scaling for different workloads very good. So let's say you're inserting a lot of data that you need indexed quickly. You can reduce how many query nodes and increase your index nodes to kind of speed up that process and kind of adapt to whatever situation you have. Also, thanks to NVIDIA and their help, we also support GPU acceleration, which is pretty great for high throughput needs. And we also kind of created our own vector search library that's open source. Anyone can modify it, add their own index algorithms. and use it within Milvus, which I think is pretty cool. And then sort of kind of going into the more general, what is vector search and how it works, we can start going over some of the algorithms used in vector databases. The first one, and a pretty easy one to visualize, is the Annoy, which is a tree-based algorithm developed by Spotify. I believe it was one of their software engineers at a hackathon created this algorithm, and it was one of the first pretty popular ones that were used. And this works by pretty much taking all your data, all your vector embeddings, and starting to create hyperplanes between them that try to equally split it in half. Doing this multiple times, you create a tree, and this tree can be used for searching. Do this, let's say 50 times, and you can create a forest of trees, and you can search in parallel through them to find your nearest neighbors. The next style is probably one of the oldest ones, which is inverted file indexes. And these come in the package face. I don't know how many people have heard of that, but that's Facebook's approximate nearest neighbor library. And inverted file indexes for vector databases are pretty much just k-means clustering. Here we have a picture of a Voronoi diagram, which pretty much represents these clusters in a 2D dimensional space. On searches, you pretty much just go, you find your nearest cluster centroids, and you search those clusters to find your top closest results. And now the most popular in all of the vector databases, services, all of whatever you name it, anything vector search is HNSW. And this is pretty much a skip list combined with a graph. The way it works is at the top of your search, you have a very sparse graph. So you make your kind of distant connections there. So you can kind of narrow down as you go down through the graph, you get narrower and narrower in the area that you're searching. And in the bottom layer is where you have your closest results. And this one is usually the fastest and the most accurate for most use cases. And that's why everyone's pretty much using this one right now. Now a little bit about reverse image search. Reverse image search pretty much comes in 3 steps. The first step is usually optional, but it kind of depends on your use case. And that first step being segmentation. And segmentation, as many of you probably know, is sort of extracting areas of focus from an image. So this is pretty much like taking out all the bounding boxes of shoes, all the bounding boxes of shirts, let's say in a photo, if you're looking for articles of clothing. The next step is generating embeddings on our images, let's say. So if we did segmentation, we would embed specifically the bounding box image of a shoe, the bounding box image of a shirt, or if you're not using segmentation, you would embed the entire image. And this just takes neural network models and kind of cuts off the last layer. And that's where you get your embedding from. You flatten out your last layer of activation. And lastly, you perform the search. And this is where the vector databases kind of come into play. And a little bit about each step is we can first start with segmentation and sort of how you can choose between which method you want to go. So if you're using no segmentation, this is usually good when you're matching an entire scene of an image. You don't really care about the really specific details. The good example of this is maybe a landscape search where everything in the image is necessary to find a similar image. Another one could be art. You sort of look at the entire image as a whole to see if there's a relatable image. For some use cases, such as clothing match from an image, it's not that great to not do segmentation because you have too much noise in your image. The model might embed, or maybe not embed, but it might kind of focus on an area of a car when making the embedding and kind of deciding the weights to give. And that might not be good because that doesn't have any semantic context for the shoe. The next step that you can probably take is generic segmentation. And this comes with models such as SAM, which is Facebook's segment anything model. This one's easier than domain specific, but not that great still. It's easier because you don't have to train up your own model. You can kind of use a generic model to segment and grab all your kind of bounding boxes, which is great because it gets you one step closer to narrowing down your search. But the main issue is you still have a bunch of extra data that you need to search through. So in the case here, where we're kind of looking for clothing only, the segment anything model is going to create bounding boxes around every object in the image. And this can sometimes result in needing better ranking methods after your search, because how do you know which image here is important? You don't want to match the closest car when you're searching for the closest pants. And lastly, there is domain-specific segmentation. And this one's the best, but it also requires the most effort because you need to train up your model to do the segmentation itself. And the reason it's great is because it extracts only what you need. You don't have to worry about any extra data. There isn't that much getting in the way when you're embedding, and it will probably give you the best results. But as previously mentioned, it requires training a custom model, which not everyone can do. So after segmentation, you get to the embedding stage. And the embedding stage sort of falls under the same problems. You can have generic embedding and domain-specific embedding. With generic embedding, you can take a resonant pre-trained model and again, get the embeddings from that. But the issue with that is that it might not always give the best results. In this case, let's say we're looking at the shoe and the shirt. It might just embed those as if it was seeing a brown and a black blob. This isn't that great because you're not really getting what you want out of the image. It doesn't really know what to pull out from the image. And this ends up with embeddings that sort of aren't that clustered too well and will give you poor results. Better results, you can use a domain-specific model where you train a model on, let's say you train a model on classifying different articles of clothing and you use that to generate embeddings of your clothing snippets from the segmentation. This will give you better results because it will kind of know what to look for within your image and will most likely generate pretty good embeddings that for similar articles of clothing, they'll be close, and for different articles of clothing, they'll be far away from each other. Lastly, the last step in these pipelines is the search step. And this is where the vector database is used. And luckily for this step, the vector search is data agnostic, meaning that you don't really care where your data is coming from. You don't care if there's noise. Every time you do a search, it's the same calculations going across all your data. With this, you ultimately kind of run into a cap theorem-like problem of you have to pick 2 out of 3 options. So you have to pick between performance, recall, and price. If you want performance and recall, then you're probably going to need a lot of memory and a lot of compute power. So this is where HNSW is. It's really good for speed and it's really good for getting a high recall, but you have to pay a lot because you're almost doubling your memory usage because you're doubling up your raw data to create the indexes. You can also go for a cheap with high recall, but that's going to be slow. And you can also do a fast and cheap model index like IVFPQ, which requires heavy quantization, but your recall drops like a rock with the less money you spend on compute. And one other trade-off that you can make are the different distance metrics for these indexes. And most vector databases and vector search platforms offer 3 types. There's IP, which is inner product, L2, which is the Euclidean distance, and cosine, which is normally the same as normalized IP. And the difference between these are just kind of comparing the distance versus the angle between 2 embeddings. For some things like text embeddings, where you kind of don't care as much about the distance, but you care more about the meaning of the word, you usually use an angle-based distance. And sometimes for images, you use the other, but this highly depends on your data and you ultimately have to kind of try it out. For this one, there's no difference in speed or price. It's usually the same, just the calculation that you use. And this is how a pipeline normally looks. You first transform your data into embeddings, you store them in the vector database, and then when a query comes in, you use the same transformations and perform a nearest neighbor search. And a little bit about other use cases of computer vision. Probably the biggest one before LLMs again was e-commerce. And a lot of this was in the form of product search. There were first people kind of did searches by matching keyword counts in descriptions of items. But then we realized we could use word embeddings and sentence embeddings to generate more semantic search results. And these semantic search results are a lot kind of closer in what the user wants when they search for something. They don't care about the keyword match, they care about what their meaning behind their search. And then after this, people kind of decided, oh, what if they want to search by an image that they already have? And this is where reverse image search was used and using these neural networks to generate embeddings on images and try to match the closest one. So like, let's say your description of a product has an image in it, you use that for the search. And lastly, they realized they can combine both with a model like CLIP. So you can kind of kill 2 birds with 1 stone and search based on text or based on image. Another popular use case or another popular field that reverse image search is used in is in law and finance. A big use case was copyright detection. So copyright detection, instead of having to go through manually, you could go get embeddings for your images and try to see, okay, these are the top 50 closest results. Let's see if this infringes on a different copyright. Allows for a lot faster discovery, and it ultimately saves money in the long run. Let's say in a lawsuit or when you're trying to copyright your new product. And also it's used in I forgot the word, but not copyright. I'll move past that. And then lastly, although not a popular one, there is autonomous driving. And this one's pretty cool. It's not too popular, as in not too many people are using it, and it's not really a sphere that vector databases are too popular yet, but it's used in situations where your model, let's say, is not too confident in what the next action should be. If it's not too confident, you might want to fall back to other actions that you've chosen before, or the nearest actions that you've chosen. So what they were doing was they were embedding their previous situations. Let's say they were embedding their camera view, and with it, they were including the action that was taken. So when you come up to another action that you don't know what to do, you can search against your previous actions. You search for a similar situation, and then you can use that action to kind of further help you decide what action to do next. Another use case for this is also, in the meantime, while you're doing that, you're also creating a new data set that you can easily label later on to train new models on, because you're sort of clustering all the similar matches. And if you don't know what the actual label for that is, later on you can label it. Next is the reverse video search situation. And this is sort of the next step in image search. And why is it hard? The thing that you can kind of think about is images are sort of solved. I might get some hate on this, but we've gotten to the point of diminishing returns on image search and image embedding generation. Yes, there are some domain-specific use cases, but ultimately you can kind of retrieve 95% of your recall and accuracy with the generic models that are already outside. The harder part about video search is that you are now adding an extra dimension, which is the time dimension. And this one's harder to kind of take into account and process on, because it requires a lot more computation to kind of compress all those frames and perform actions on them. Another thing is that there are long-term dependencies in video that need a way to introduce memory into your models. And this can kind of get difficult, and I'm not sure if it's there for videos yet. And also there's a lot of lack of meaningful data for video search. LLMs were kind of taking off because you don't actually need labeled data for it. It's kind of take all your unlabeled data as much as you can get and push it through the model. Video doesn't have this yet. So luckily there are some models that we can use for this, and the general process is similar to reverse image search. And there's just an extra step of breaking the video down into frames and grouping the frames together and then performing the embedding. There are a few popular models currently that can be used for this. There is the Clip for Clip, which is a model based on Clip, which allows for text to video search. There's X3D, which is an expanding model. It's sort of like a 2D model, but it expands in all the dimensions, both in resolution and in temporal dimension. And there's Video May, which is based on an autoencoder for videos. And in production, a few of the popular use cases that you can normally see are large-scale video search and video recommendation, scene deduplication, and similar to video recommendation, there's targeted advertising. And I'll go over a quick demo. Hopefully it's working right now. And hopefully you can see this in the video. But this is a quick example of kind of this segmented image search. As you can see, you first can run your images through a segmentation model to get out the bounding boxes. And then later on, let's say you want to search for, based on these bounding boxes, let's say I want to search for a similar shoe. I can go and perform a similarity search. Oops. Let me reset this. And yeah, there is, you can see, you can do the reverse image search for the nearest shoes. And let's say you want to see, I believe you can show just the entire image of where that image was found. And yeah, so that's a quick demo of sort of what it looks like. The code for this is pretty simple. What it involves is first getting the segmentations from your image. This can then get turned into a mask. And with the mask, you can get your bounding boxes. And then with these bounding boxes, so you go through your data, you generate your bounding boxes. And then in voxel, you can save those bounding boxes as detections, which can ultimately be converted to patches, which you can then do your similarity search on. So the patches in this case are these image cutouts. Pretty simple pipeline. Yeah. Let me get back to this. So getting started, if you want to check out some more projects, some more and how to use this, here are a few links. And this should link you to our site and with some more resources for this as well.